Okay, so we're going to finish up section 4.5. This is going to be the last group of examples we're going to look at. So we're going to start out with limits at infinity. There's a L'Hopital's rule for that. So this is going to be theorem. We're going to say assume that f of x and g of x are differentiable on an interval b out to infinity, and that g of x is not equal to 0, or sorry, g prime of x is not equal to 0 for x greater than b, if limit x goes to infinity of f of x and limit x goes to infinity of g of x exist and are either both 0 or both infinite, then we get the following thing, which is going to be another statement of L'Hopital's rule, except this time instead of x going to a, x goes to infinity, f of x over g of x. So if we look at the limit of that, that equals the limit as x goes to infinity of their derivatives. Oops. So this is our equation that we're going to kind of be looking at for the next few examples. And this is true assuming the limit on the right exists. And you get a similar result. Holds for limit as x goes to negative infinity. So if instead of going to positive infinity here, if you're heading off to negative infinity, you'll get a similar, you can use basically a form of L'Hopital's rule like this and get it to work as well. All right, so we're going to finish up doing a couple of these examples. So we're going to say which of f of x equals x squared and g of x equals x natural log of x. We want to say which grows faster. So what we're going to do is we're going to look at the limit as x goes to infinity of f of x over g of x. Now, if that limit is equal to infinity, then f of x was growing faster than the bottom, so that pulled the thing up to infinity. So f of x grows faster. If the bottom is getting larger than the top, that's going to create a fraction where the bottom gets larger and larger and larger. So we get if that thing here equals 0, then g of x grows faster. So basically, we're comparing these. We're going to compare these two, and we're going to see does the limit of them approach infinities or zeros. So we'll say, all right, limit as x approaches infinity of f of x over g of x. That's limit as x approaches infinity of f of x is x squared. G of x is x natural log of x. As you head out to infinity on x squared, that is infinity. As you head out to infinity on x, that's infinite, and natural log of x is infinite. So we're in the form infinity over infinity. So we can't compare it yet because we're in this indeterminate form. So we're going to have to apply L'Hopital's rule. So we're going to use L'Hopital's rule at this step, which will have us take the derivative of the top, which is 2x, And then we're going to take the derivative of the bottom. So we're going to have to use the product rule for the bottom because we've got two things multiplied together. So I'm going to leave x alone, take the derivative of natural log of x, which is 1 over x. Then I add to it, the derivative of x is 1 times natural log of x. So I'm going to simplify this up a little bit, and then we'll see if we can compare the limits yet. So we have 2x over x times 1 over x is 1 plus natural log of x. As x goes to infinity, 2x goes to infinity. As x goes to infinity, natural log of x goes to infinity. So something going to infinity plus 1 goes to infinity. So we're still in this form, infinity over infinity. So we've got to take L'Hopital's rule a second time. So derivative of 2x is just 2. Derivative of 1 is 0, so that goes away. And the derivative of natural log of x is 1 over x. When you have 1 over x down in the bottom, you're able to shift that back up to the top. So this will be the limit as x approaches infinity of just 2x, which is infinity. So that means the top function grows faster. So that means, we got it equal infinity, so that means f of x grows faster than g of x. And a way in symbols we could write that so that you don't have to write it out. Each time you could say g of x, you put kind of this double less than, so g of x less than f of x means the g of x function grows slower than f of x, or you could say the f of x is growing faster than g of x. And if we write it back just to what they actually were, x natural log of x grows slower than x squared, or we could say x squared grows faster than that. So we got our answer down here. Okay. So we're going to do one more of these, and then we have one last statement, and then that's going to kind of wrap it up for section 4.5. So, this is example 10. So, for example 10, we got Jonathan's interested in comparing two computer algorithms. So, let's say John compares two algorithms. We have one of them has runtime that's about, we'll say, natural log of n squared, and the other has runtime square root of n. And we want to say which algorithm takes less time for large values of n. Okay, so basically we want to know, does natural log of n squared or square root of n, which one grows faster than the other? So I'm going to put natural log of n squared up on the top, and I'm going to put square root of n down below, and we're going to look at the limit as n approaches infinity. So we want to look for large n, so we won't let the n's run off to infinity and get large. And then again, if this equals infinity, then natural log of n is, natural log of n takes more time, so natural log of n will be much bigger and growing faster than n. Remember, this is runtime, so big runtime is not going to be good for an algorithm. You want the algorithm that runs faster. So in this case, if it goes out to infinity, then the top thing is taking longer to run, so you want to choose the bottom. If this ratio equals 0, then square root of n will be the longer running thing, and you want to choose the other one. So we start out here, and we're going to say, all right, natural log, as you got to infinity, that goes out to infinity. And if you square it, stuff going to infinity squared goes to infinity. Square root of stuff going to infinity goes to infinity. So we're in this form, infinity over infinity, which is this indeterminate form. So we're going to have to use L'Hopital's rule. Which means take the derivative of the top and take the derivative of the bottom. We're going to have to use the chain rule for the top, so I'm going to bring the 2 down. We're going to get natural log of n. So it's bring the outer function down, leave the inner function alone. Then we have to take the derivative of the inner function, which is 1 over n. Derivative of natural log of n is 1 over n. Square root of n, that's n to the 1/2 power. We'll use the power rule there. We'll get 1/2 n to the negative 1/2. So now we're going to do a little bit of some algebraic stuff. If you're dividing by a half, that's the same as multiplying by 2. So we're going to get limit as n goes to infinity of 4 natural log of n. And if in the top, if you have a fraction 1 over n and you're dividing that in the top, that can move downstairs. So we'll have n to the negative 1/2 times another n. So that'd be times an n to the first power. So we get this is limit as n goes to infinity of 4 natural log of n, all that over n to the negative 1/2 times n to the 1 is n to the positive 1/2. If we let n go to infinity again, infinity, stuff going to infinity times 4 goes to infinity. Infinity to the 1/2 power also goes to infinity, so we're back in this infinity over infinity form. So what we got to do is use L'Hopital's rule again. All right, so the top becomes 4 times 1 over n. Since there's no power on natural log of n anymore, we didn't need to use the chain rule. The bottom becomes 1/2 n to the negative 1/2. This 1 over n can move downstairs again, so we get limit n goes to infinity of 4 over, dividing by 1/2 again, we can push that up top and make that a multiply by 2. So we get 8 over, this is going to be natural log of a half times another n. Sorry, natural log of negative a half times an n to the first. That'll be natural log of positive a half down there. And then as we let n go to infinity, this will be 8 over bigger and bigger and bigger fractions, which is going to tend towards 0. So since that happened, that says the bottom is growing faster than the top. So that says square root of n is growing much, much faster than the top, which was natural log of n squared. Sorry, it's supposed to be just a regular inequality symbols. So natural log of n squared takes less time, so we'll say choose the algorithm with runtime natural log of n squared as it takes less time. So the runtime based on square root of n is much, much bigger than the runtime based on square root of n squared. So we want to choose that one. And that's basically our answer to that. And then to finish the section off, we have one last little note that we want to make. This is a theorem. And so we're just going to state it, and just that'll be a good thing for you all to know. This is growth of e to the x. And so x to the n grows slower than e to the x for every exponent n. So basically, x to the power n, if you got to infinity, e to the x eventually will always grow faster than it. So we could say, in other words, if we compare the limit as x goes to infinity of e to the x over x to the n, e to the x grows faster, so this is going to equal infinity for all n. So it doesn't matter what power, if you put 100 in there, or 200, or 1,000. So yeah, you're looking at like x to the millionth. E to the x eventually grows faster than all of them. All right, so that's going to do it for section 4.5. Stop there.